Okay. Hi, Precalc C. More learning, and this is another thing which you learned in Precalc A, but it was in the Precalc A curriculum, but it's sort of also in the Precalc C curriculum, and I bet there are some of you, probably a very small number of you, who are already kind of perfect at this topic, but everyone needs to be perfect. So I'm going to teach you how to do this. We're going to review some of these basic things, and then by the end of this video, plus some more practice, we're all going to be very, very good at this topic, because it's actually a really important and useful skill to have. Okay, here we are. I got this inequality. So 7 over x plus 1 plus 1/2 is greater than or equal to 51 over 4x plus 10. Okay, this is problem 1 from a packet called Inequalities Review, which I will have you download. So we're going to sort of talk this out right now, and I think you do this, in week 3 or something of Precalc A. Okay, what's going on? Well, I want to find all values of x for which this sentence is true. Okay, and you can sort of make some cursory observations, like if x is -1, the whole thing is undefined, so that can be. So maybe you even want to kind of note that, right? That x can't be -1, and x can't be whatever that is, -5 halves, because if x is -5 halves, then that blows up. Okay, but trying to reason out any further, it's just getting too complicated. So we need to kind of do something with this algebra. What can we do? Well, if this were an equal sign, then there is a really good way of simplifying this very quickly, and that would be to multiply both sides by x plus 1, for example. If you multiply both sides by x plus 1, then you're simplifying, you're getting rid of fractions, you're making it making kind of progress. All right, but this is something that you have to tell Precalc A students. Since we're solving this inequality, we absolutely cannot multiply by x plus 1 because, basic review of solving inequalities, if you have some kind of inequality, say of 2 positive numbers, and you multiply both sides by 5, then you get, 10 is less than 15. So it seems like I'm allowed to multiply both sides by 5, but of course, if I try to multiply both sides by -5, then the relationship between -10 and -15 is that -10 is greater than -15. Okay, so we have to be very careful when we're doing Algebra 1 with inequalities that when you multiply both sides by a positive, the inequality is preserved, and when you multiply both sides by a negative, the inequality is flipped. This is not some kind of mystery, by the way. If you have A is less than B, and A and B are both positive, and you want to multiply by -c, say, and you want to sort of know why that works. Okay. So why does that work? So suppose C is negative. Okay. Well, if C is negative, then the opposite of C is positive. And as we've seen, when you multiply both sides by a positive number, the inequality is preserved, which of course just makes complete sense because if you have something like A and B, if you want to think about this geometrically, I'm getting a little bit off topic now, but if that's A and the whole thing is B, so this is a kind of geometric proof. When everything is positive, it's possible to just do geometry. So let this short segment be A and let this whole segment be B. Well, if B is greater than A, then of course we have now this rectangle, and this is some number like D or something. Then this is AD, this rectangle, and then this whole thing would be BD. Okay, so in other words, I'm trying to convince you that if B is greater than A, then of course BD is greater than AD. That's sort of just an obvious fact about positive numbers. That one, which is this one, is sort of not under question. The one that students find confusing is this whole multiplying both sides by a negative thing, and I'm trying to convince you that it's just not confusing at all. Because if C is a negative number, then the opposite of a negative number is a positive number. So negative C is positive. Well, if negative C is positive, then you can just multiply both sides by a positive for the reasons that we just discussed. And now you just have negative AC is less than negative BC, but then you just add BC to both sides, and you just add AC to both sides, and now if you really want to, oh well there, hold on, something happened. Add BC to both, multiply by negative C, then, am I done? Oh, and then, and then just flip this back, right? So if BC is less than AC, then it means that AC is greater than BC. Sorry, I confused myself for a second. So this is just an explanation for why, in case you never got this in Algebra 1, this is the explanation for why when you multiply by a negative number, you flip the sign. It's not mysterious. You're not really flipping the sign. You're just, things just end up on the other side, and then you just kind of put them back. Okay, why is this relevant to us? Because I don't know whether x plus 1 is positive or negative. I don't know what x is. In fact, I'm considering every possible real number value of x plus 1. So since I don't know whether x plus 1 is positive or negative, if I can't multiply both sides by x plus 1, because it would matter whether x plus 1 is positive or negative if I flip the sign or not. So that would lead to all kinds of terrible kind of casework. Oh, if x plus 1 is positive, flip the sign. If it's not, it's negative. That's just too hard. And therefore, okay, I apologize if you knew all this already, which you really should have. Therefore, when solving inequalities, that is not what we do. What do? We keep the entire thing all together. And so, the way to do this problem is very slowly and neatly and carefully. We have 7 over x plus 1. I'm going to leave some space here and write this as 1/2. And leave some more space, and this is greater than or equal to 51 over, let me factor this as 2x plus 5. Okay, and why am I being so sort of careful? Because now what I want to do is to get a common denominator. And what is the common denominator of x plus 1, 2, and 2x plus 5? Well, it's going to be x plus 1, 2x plus 5. So there are a couple different ways to do this, but I think the best thing to do, or one thing to do right now, is to multiply this 7 over x plus 1 by 2 over 2, and also multiply by 2x plus 5 over 2x plus 5. This is the kind of thing that you do in Precalc A, and this was 1/2. And then what do I need to multiply 1/2 by to get the common denominator? Well, I need to multiply by x plus 1 over x plus 1 and 2x plus 5 over 2x plus 5. Okay, and what do I need to do over here? I need to multiply by x plus 1 over x plus 1. Alright, so this is like the careful person's guide to, doing Precalc A or something, where you write it all out nice and neatly like this. Well, it's clear that when I expand this all out, I'm going to get a common denominator, and so that's good. Alright, so let's just do it. If we distribute through, that's 14 times 2x, so that's 28x. 14 times 5 is 70, plus, multiply these out, that's going to give me 2x squared plus 7x plus 5. And then, well, okay, sure. Then greater than or equal to, all of this is over 2x plus 1, 2x plus 5. And over here I have 51x plus 51 over 2x plus 1, 2x plus 5. Okay, now I have a, now I can just move everything over to one side. That's how we handle this. So okay, let's just see. Can I do this all in one step? Maybe I shouldn't or something. So okay, what do I have? 2x squared plus 35x plus 75. But then I will subtract 51x and I will subtract 51. And all that is less than or equal to 0. So this is all over 2x plus 1, 2x plus 5. Okay, continuing to simplify, what do I get? 2x squared, 35x minus 51x, that's minus 16x. 75 minus 50 would be 25, and minus another one would be minus 24, so plus 24. All over 2x plus 1, 2x plus 5 that should say greater than or equal to 0. So this is just total algebra, just algebra. I can even divide the top and bottom by 2, so that will give me x squared minus 8x plus 12 over x plus 1, 2x plus 5. And that can be factored as, of course, x minus 6, x minus 2 over, and by the way, some people like it, you don't have to do this, but maybe it's helpful to some people to factor 2 out of this. So it's really like 2 x plus 1, and then that's really like x plus 5 halves. Okay, I just did a lot of algebra, very sort of slowly and carefully, and maybe I'll write my kind of final step or something up here, because there's even one more thing I could do, which is I could just multiply both sides by 2, in which case that 2 is just gone. Okay, so this entire problem just boils down to x minus 6, x minus 2 over x plus 1, x plus 5 halves. And now is greater than or equal to 0. Okay, so, and actually everything we did up until now was kind of just, I don't want to say a waste of time, it was just kind of practice, doing more algebra, thinking through, solving inequalities or whatever, but there was no real deep thinking involved. It's just the strategy you had to pursue of kind of being careful, getting common denominators, moving everything over to one side, simplifying, factoring, etc. Okay, but now the thinking really starts now. I guess, you know, in the language of September, I would say that these two inequalities are equivalent. Any solution to this inequality will be a solution to this one and vice versa. So all the real thinking happens now. So okay, I will actually erase all of this, because the skill that I really want to practice is this skill, which is also something that you learned in Precalc A. And the skill is, how do we solve inequalities like this when they're already factored? Okay, how do you do this? Well, there are some strategies, and everyone teaches this kind of slightly differently. So I think Mr. Kirk has a certain style. I'm going to teach you my style, and it should, hopefully you agree that it's basically the same thing. I'm going to call this the long way, because I'm going to do this once, and then I'm never going to do this again, and nor should you ever do it again, because it's really, really long. The only good thing about it, this is how I used to teach it when I taught Precalc A, the only good thing about it is that it's completely clear and obvious sort of why it works, but it does take sort of forever. Okay. Let's go. What is the long way? The long way says, dude, I need to solve this inequality. Well, I want to know when this thing is positive. What is this thing? Well, it's a fraction. Well, when is a fraction positive? Okay, well, a fraction will be positive when either the numerator and denominator are both positive, or when they're both negative. Okay, so that means I need to know whether I need to know the sign of the numerator and I need to know the sign of the denominator. Well, each of those is a product of two things, and okay, if they're both positive, then, or both negative, it's positive, blah, 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 blah. Okay, by thinking about this for 20 seconds or something, I realize that getting to the truth of this is going to require me knowing for each of these four factors under precisely what conditions it's positive and negative. And therefore, the entire sort of number line of real numbers breaks down in a kind of a way. And what we say is, all right, well, let's just consider all the relevant numbers. One set of numbers, let's see, maybe I'll do it like this. One set of numbers are all the numbers from negative infinity to negative 5/2. Okay? Another set of numbers are all the numbers from negative 5/2 to negative 1. Another set of numbers are all the numbers from negative 1 to 2. And another set of numbers is all the numbers from 2 to 6. And then there are all the numbers from 6 to infinity. Okay, and that kind of covers now the entire number line. And what I've done here, what I'm about to do, is to make a gigantic, annoying chart. And I said we're never going to do this again. So, okay, promise. But the chart is actually great. What the chart is going to do is it's going to look at each of these factors, x plus 5/2, x plus 1, x minus 2, and x minus 6, and then the entire expression, x minus 6, x minus 2, over x plus 1, x plus 5/2. And what we're going to do is we're going to analyze the sign of each of these expressions for each of the numbers on these intervals. So okay, let me finish this off. Alright. This is, by the way, how I think this subject should be taught to people learning this for the first time. Okay, well, maybe what's the simplest case? Maybe the simplest case is the expression x minus 6. Okay, well, when is x minus 6 positive and when is it negative? Well, if x is bigger than 6, it'll be positive. So for numbers from 6 to infinity, it's going to be positive, of course. But anything less than 6 and x minus 6 is going to be negative. So for numbers which are, if x is negative, it's certainly going to be negative. And even if x is between 2 and 6, it's going to be negative. This doesn't start becoming positive until we get to 6. And x minus 2, kind of a similar thing, right? If x is bigger than 2, it'll be positive. So we expect numbers on the interval 2, 6, and anything above will be positive. But until I hit 2, x minus 2 is going to be negative. Okay, how about x plus 1? If x is anything more than negative 1, like negative 1/2, say, then we're positive. And on up, right? So this x plus 1 factor is negative until, this x plus 1 expression is negative until we get to negative 1, positive thereafter. And x plus 5/2 will be negative if x is something less than negative 5/2, but if x is something more than negative 5/2, it will be positive. Okay, so by tedious analysis of every case, I now can conclude something about numbers on the interval negative infinity to negative 5/2. All of the factors, all four of them, are negative, and so the product is positive, or the whole expression is positive. Here I have sort of 3 negatives and a positive, so when I multiply and divide them all together, I'm going to get negative. Here I have 2 positives and 2 negatives, so when I multiply and divide them all together, positive, negative, and positive. Alright, and so basically, I am actually now just done with this problem, because what did the problem ask? The problem said, find all the x values for which this is greater than or equal to 0, and the answer to this whole thing is just going to be, well, these 3 intervals. So everything from negative infinity to negative 5/2, and everything from negative 1 to 2, and everything from 6 to infinity. And now I just need to check the endpoints, so to speak. Well, if x is negative 5 halves, exactly negative 5 halves, is that a solution? Well, no, because that's going to crash the denominator, and so that will not be a solution. So open. So in other words, exclude negative 5 halves. How about negative 1? If x is negative 1, is that a solution? Well, no. Once again, we're going to blow up the denominator. But if x is 2, well, now that's 0, so the whole thing becomes 0, and 0 is greater than or equal to 0. So 2 should be included, and similarly 6 should be included. Alright, so we're done with this problem. It took like, 10 minutes or something, or more, a lot more maybe. But that is the answer, and that's how you do this. Alright, the short way says, I don't really need to do all of this. As long as I am very skilled about polynomials. I'm going to call this thing up here like Roman numeral 1 or something. This is my inequality. Well, what I'm now going to do is I'm going to propose to you a second inequality. This inequality is, well, I'll just give it to you right now. It's x minus 6, x minus 2, x plus 1, and x plus 5 halves is greater than or equal to 0. Okay, well, great. A couple things to say. This is an inequality, so okay, we can solve it somehow. It is related to, but different from this inequality above. In fact, this is just a polynomial. The entire left-hand side here is a polynomial, something we're kind of an expert on. But this is definitely not a polynomial. It's called a rational function. It's a way more complicated thing. And this function is going to look nothing like this function here on the left. But, and maybe this is obvious to you, when I am solving this inequality up here, all I really care about is when these four expressions are positive and negative. I don't actually care what their value is, only whether they're positive or negative. But here, this inequality, when solving this inequality, these four factors are going to be positive and negative in the exact same places. In other words, if this is not already obvious to you, I need to encourage you to think of this second inequality and this first inequality as being basically identical. Okay? Totally different functions, but the solution to this is the exact same thing as the solution to this, give or take a finite number of points. And another way of putting it is, what am I really searching for here? I'm searching for, when there's kind of, the answer to this is when there's sort of an even number of positives and an even number of negatives among these four factors. But over here I'm searching for the exact same thing. Maybe even a more visceral way of putting it is, suppose I had just been presented kind of out of the blue with this Roman numeral 2 inequality and told to solve it the long way. How would I solve it? I would make the identical chart, right? I would divide out my real numbers in the exact same way, column-wise, and the first four rows would be the same, and then the only difference would be right here. I would put the product of those four numbers instead of the combination of product and quotient. And the thing is, it just doesn't matter. And so what I will propose, kind of like for now and forevermore, is that when solving inequalities of type 1, we just basically skip right to inequalities of type 2. And I now say that inequalities of type 2 are trivial and can be done in 30 seconds without actually making this chart. Because this is just a polynomial. And dude, we just know polynomials. Specifically, what does this polynomial look like? Well, it has a root at negative 5 halves, it has a root at negative 1, and it has a root at 2, and it has a root at 6. Oh, what's the leading coefficient? It's positive. So the end behavior is like this. And therefore, this thing is just going to look like that, just like fact. And therefore, this polynomial will be positive for numbers to the left of negative 5 halves. It will be negative between negative 5 halves and negative 1. It will be positive between negative 1 and 2, negative between 2 and 6, and positive thereafter. Someone was mentioning this last week when we were discussing, at a very low level, why we know that this polynomial looks this way. And actually the best answer for why we know that this polynomial looks like this is this chart, right? This chart is the real answer for how we're sort of sure about when this polynomial is positive and negative. But once you make this chart once, polynomials are just so easy and simple and well understood, well-behaved objects that personally I don't think you need to make this chart ever again. This is just a polynomial. It's a quartic. It has 4 roots. Those roots are all linear, single roots. So the function will be locally linear at each of those roots. In other words, it will cross the x-axis and change sign. So when I look at this, I just say, okay, you know, it's just going to go like this. So it's going to be plus minus plus minus plus. Boom, done. And now, when it comes to solving something more complicated than this, here's what I would actually do in the future when faced with this Roman numeral 1. I would just make my number line, go, just put in -5/2, put in -1, put in 2, put in 6, and now just sort of picturing the polynomial in my mind, it is a quartic. I will just answer that this problem is has sign distribution plus minus plus minus plus, and then just call the problem done. And then when it goes to write my final answer, I'll do what I did sort of here, and I still do have to take care to include or exclude the appropriate edge points, and that the edge points are the only difference between inequality Roman numeral 1 and inequality Roman numeral 2. Okay, so this was a very long, slow, careful, patient explanation of how to solve inequalities and how to do it kind of the fast way. Feel free to just stop watching now, but if you want some more help, I'll just do one more problem from the packet. I'll do number 2, and this time I'll do it, you know, only the fast way, just so you can see how it goes. All right. So here we go. We're given some function, and here's the function: the square root of 3x plus 1 over x squared minus 1 minus 4x over 2x squared plus 2x. Okay, and the question is, what is the domain? Okay, so wow, what is the domain? Well, this basically just boils down to, you know, when is 3x plus 1 over x squared minus 1 minus 4x over 2x squared plus 2x, when is that going to be greater than or equal to 0? I'm going to just solve this equation, and whenever that's true, then that will be an x value that I can plug into this function. Okay, so let's solve this inequality. How do we do it? First, we can just factor as much as possible to prepare for getting a common denominator. So this is x minus 1, x plus 1. And this is minus 4x. Okay, there's a little twist here. So I'm going to factor out a 2x, and that gives me x plus 1. Okay, so you might be tempted now to divide the top and bottom by x and just kind of get that stuff out of your face. And I think that's okay, right? X over x just really is 1. So it is legitimate to cancel it, but we need to be careful that, of course, x can't be 0. So just writing that up on the very top of the page, right? X can't be 0. So, all right, so I'll just do that then. So this is 3x plus 1 over x minus 1, x plus 1. And this, if I cancel the 2's as well, this ends up just being 2 over x plus 1. All right, so that's looking a lot simpler now. Well, how do I solve this? Just get a common denominator and just take care of it. So I'll multiply by x minus 1 over x minus 1. I think this is actually an easier problem than before. So what do I get? 3x plus 1, being careful with my parentheses, that's minus 2x plus 2 all over x minus 1, x plus 1. And okay, this numerator just becomes x plus 3. Alright, so here there was less algebra to do, and now, in my opinion, this is where the real thinking starts. And the thinking for me goes like this. This is not a polynomial, of course, but it reminds me of the polynomial x plus 3, x minus 1, x plus 1. And though these two functions are totally different from each other, they are positive and negative in all the exact same places. Because what's determining whether this expression is positive is just when x plus 3, x minus 1, and x plus 1 are positive or negative. And in this polynomial, those three expressions are positive and negative in the exact same times. Therefore, this is a much easier polynomial, this is a much easier inequality to analyze because the left-hand side is a polynomial and because polynomials are easy. So since polynomials are easy, I don't even need to draw a picture of the polynomial. I'm just going to say, okay, what are the key points are negative 3, negative 1, and 1. What is this polynomial? It's a cubic. The leading coefficient is 1. If the leading coefficient is 1, the end behavior is like this. If the end behavior is like this, then the thing starts negative, and then becomes positive between negative 3 and 1, negative thereafter, positive thereafter. That just is, if you prefer to like, some people like to sort of draw in the polynomial. I don't do that, but some people like to. But this is just what cubics do with respect to their locally linear single roots. And therefore, the answer to this problem, when is this positive, is going to be everything between negative 3 and negative 1, and everything from 1 to infinity. And when it comes to answering the question for the particular numbers, that's when I have to look at the real inequality, which is this one. And of course, if x is exactly equal to negative 3, then the numerator is 0, so the fraction is 0, so that is a solution. So I should include negative 3, but if x is 1 or negative 1, this thing is undefined. So I should exclude 1 and negative 1. And notice that even though x can't be 0, 0 happened to land here in no man's land, so I've already just done, and this problem is just done. So there's no need to ever do this the long way, ever again. The long way is very long, time-consuming, sort of tedious, annoying, and you're kind of missing the whole point. And really, when we get here to a problem like this, you should be able to get to the answer in 1 minute or something like that or less. Okay, good. For homework, you're going to do some more of these. Bye.